Great, okay. We'll get started. Before we get to the main lecture, just a couple of administrative updates. So I'm going to be holding my office hours starting next week. It'll be from 10 to 11 on Mondays, and then Facundo, our TA, is also going to be having office hours 2 hours a week from 6 to 8 p.m. on Thursdays. If you're not able to reach us at those times, you can feel free to send either Facundo or I an email. The office hours are going to be held on Zoom virtually, and I'll set up the meeting details and post them on Canvas, and Facundo will do the same. As I had mentioned before, there's going to be supplemental sort of optional reading for any material that folks are more interested in, and I'm going to start posting those on Wednesday. Lastly, I'm still waiting on some of the mentors for the final project for their descriptions. Hopefully we'll be able to get all of those in by Wednesday. And I'll quickly go over during that lecture what all the projects are and maybe a little bit about the mentors themselves. The project assignment, I'm going to send out a Google poll. And if you fill that out and rank your top 5 options, hopefully we'll be able to accommodate everyone and distribute people into groups and projects that they're interested in. And so once the description has been posted, I'm gonna put up that poll, and everyone can read through all of the projects, learn a little bit about background on the topics, and decide on what you're most interested in. And we'll have a deadline on the polls. If you don't fill it out, you'll probably just get assigned randomly into a project that needs it. So please do make sure to fill that out. Okay, so let's go ahead and get started. We'll pick up actually where we left off last time. So real quick, this is the reference sheet that I showed for both unit conversions, some efficiencies, and to look at energy content. So I had gone over how to derive electrical energy from the first one. We'll quickly cover these next two and then talk about some ways of putting together the dimensional analysis, make sure that that's clear in your mind, as well as I really briefly mentioned last time, significant figures, which is something that you'll need to pay attention to in the homework, but also for whatever future analytical work that you'll be doing. It's a important procedure to keep in mind. Okay, so how much electrical energy can be derived from 30 kilograms of dry biomass? So we'll start by converting our biomass here into its energy content, and then we multiply to translate into the energy content for electricity in the same unit so that we can multiply by the efficiency of production. Okay, so we can always sort of safely start with our given, so 30 kilograms. If I just really briefly go back to the reference sheet, I can see here the energy content is in gigajoules per ton, which I'll need to keep in mind. So I need to translate my kilograms into tons. And then, as we know, since electricity is always in kilowatt hours or megawatt hours, I need to use this conversion down here, gigajoules, equals 277.8 kilowatt hours to get it into the same units. Okay, so 30 kilograms times 1 ton per 1,000 kilograms. And just as a quick note, the nomenclature for tons versus tons will try to be as consistent as possible. So tons, like spelled like this, is imperial, and that is 2,000 pounds. Whereas tons here is metric, and that's 1,000 kilograms. Okay. And as we saw from the reference sheet, you can get 18 gigadoules per ton. And we need to translate it, as I mentioned, into kilowatt hours. So 277.8 kilowatt hours divided by gigajoules. Oop. Okay, and so that translates this into kilowatt hours of biomass. And if we want to change that into electricity, we can do the efficiency of conversion. So this is basically burning the biomass to turn it into electricity. So that's 35 kilowatt hours of electricity for 100 kilowatt hours of biomass. And so this is the same thing as just multiplying it by 35% or 0.35. Okay. And so this results in 52.5042 kilowatt hours, which I would report as about 53 kilowatt hours. Okay, so pretty straightforward. A couple things to just keep in mind is that whenever to sort of avoid confusion with these dimensional analysis with unit conversion, the best way to keep track of these things is to be canceling out your numerator and denominator units so that you can be sure that you are doing the unit conversions correctly, right? So here I can even get rid of the kilowatt hours biomass, turn it into kilowatt hours of electricity, which is what we want at the end. Okay, and then the other point that I was going to make is about significant figures, which is in the final reporting. I'm showing a total of 2 digits here. And this is a pretty important concept. It seems kind of trivial, but when we're talking about really doing engineering problems, if you were to report this sort of number, you're kind of implying, right, that I have knowledge and accuracy about this last thing up to the last digit that I'm reporting. And so there's some uncertainty here, right? And so if this could vary by, plus or minus 1 kilowatt hour versus plus or minus 0.1 kilowatt hour versus 0.01, that is telling a fairly sort of different level of precision in my answer. And so having report out to the 10,000th place or thousandths place, really what you're saying is that I am confident that 30 kilograms of dry biomass is going to get me, exactly up to this level of accuracy plus or minus something in the last digit, which is at a level of confidence higher than really what you are given in the data. And so the general rule of thumb is to look at your actual equation here and identify which unit gives the least precision. And so in the actual conversions, which is like these values here, some of them can be exact, right? So 1,000 kilograms, that could be 1,000.000. But the main thing that we want to be concerned about is the inputs. And so our main inputs are going to be the 30 kilograms, the 35% efficiency. That has 2 digits in them, and so in the final answer, you want to report as 2 digits, and that's a really sort of critical way of presenting your solutions with the right level of precision. And so definitely keep that in mind for when you're working on the homework. That will be something that we're looking out for. Okay, great. So finishing up the last example, we'll just finish this. So 1,000 cubic feet times 1, oops. Times 1 gigajoule per 1,000 cubic feet times 277.8 kilowatt hours per gigajoule times a conversion efficiency of 55%. And this is equal to 152.79 kilowatt hours, which if we use our significant digits, in this case, our limiting factor is the efficiency here. So that's 2 digits. So our final answer would be reported as 1.5 times 10 squared kilowatt hours. Okay, same principle as before, cancel out the units, make sure that we have everything lined up nicely, and that'll be our sort of last example for dimensional analysis. Okay. So we can move on. Let me clear the board here. To the main topic of today's lecture, thinking about economics and financing for energy systems. And hopefully this will be pretty clear why this is important. The economics of the systems are really what drives a lot of the decision making. And that can have lots of impacts on how we deal with problems like climate change. And we'll get into more detail about that in a moment. Okay. So how much does it cost to produce, store, transmit, and use electricity? Oh, yes. Are the slides posted? I guess I haven't posted these yet, but I will post them immediately after lecture. Sorry about that. Okay. How does the cost of one energy technology compare to another? What factors determines the cost? So types of questions that we might want to answer with these engineering economics. So a wind turbine operates for 10 years. What's the cost of the electricity it produces? You can even think of this on a more sort of personal level. If I want to decide to install a solar hot water heater on the house, does that make sort of financial or economic sense? When we think about a company making an investment in energy conservation, what's the value of the energy savings? How long does it take to repay the investments? And that could even be a single point of decision, right? But there could be other decisions about different types of investments that a company might want to make. And so this whole procedure will help understand how to do that. Thinking about comparing the cost of owning and operating an electric versus a gas car. And also how can we include costs of environmental externalities like pollutants, like carbon emissions. How would that factor into sort of economics and financing questions? Okay, so cost versus price. One thing, quick bit of nomenclature to clear up. Sometimes this is used interchangeably, but really when we're talking about economics, they mean pretty sort of distinct things, right? So the cost is the amount of money that we sell the energy for to make a desired rate of return or profit on our investment. I guess the sort of better way to think about cost is how much money it takes to produce something. And then the price of energy is basically how much people pay for it. And so price doesn't always equal cost, right? It costs some amount of money to produce electricity, to produce a car, but then when you sell it to the consumer, market forces based on supply and demand are the things that determine the price of it. And you could end up paying more money usually than it costs, or you could pay oftentimes the same amount as it costs. And sometimes, in some rare exceptions, you could actually, be paying less than the cost of how much it takes to make it. And oftentimes, those types of things would be subsidized by the government, for example. Otherwise, the company that's producing whatever it is that you're buying, if they're constantly selling. If they're selling goods at a price that is lower than the cost of what it takes to produce, then they'll eventually go out of business. But a good example of this is like electric vehicles. For a long period of time, the cost to produce the electric vehicle, because the battery is so expensive, is actually a little bit higher than what the companies are selling it for. And there's various reasons for why they're doing that. But that is an example of where the price actually is lower than the cost. But typically that'll be pretty rare. Okay, time value of money. So this is kind of interesting concept. I remember when I was in grad school learning about this, it was fairly sort of unintuitive that the worth of money changes over time. And that's not even just sort of accounting for sort of inflation, right? And so there's this question that I'll often pose. So, if I were to give you, $1,000 today, would you rather have that today than, say, next year? So a year from now, and of course, everyone always chooses to take the $1,000 today, and that's kind of the logical decision, right? Because I could, for example, take that $1,000 and just stick it in the bank for a year, and I would earn a little bit of interest. And so a year later, that $1,000 should be worth more to me because of the interest that I've made on the money. And so over time, if I look at a quantity of money today versus a quantity of money in the future, current day money is basically always more valuable. But the way people value money over time is oftentimes not straightforward and can differ both from person to person and even from even from based on different activities and different quantities of money, and so not always so straightforward. And so to get at the value that people place based on time, we need to compare present costs and future costs on the same time basis. Okay, so what does this mean? There is a type of economic and financial analysis called present value or present worth analysis. So the concept of time varying value of money is known as discounting, and it takes this concept called discount rates, which is essentially an index for the rate of change of the value of money. People will have some of these related terms, such as interest rate, cost of capital, opportunity cost of capital, internal rate of return. All of these concepts are sort of related to the discount rate, but you can think of it basically as how the value of money changes over time. It's not specifically, it's not equivalent to the inflation rate, and it's not equivalent to interest rates because discount rates are not uniform for different entities. Both of them will have an influence on discount rates. And so, for example, if we were thinking again about your personal discount rate, then, you know, that example that I was saying where you could just take the money and stick it into the bank, well, if banks were giving, you know, like 10% interest versus 5% interest versus 1% interest, your value for the discount rate would change probably in accordance with what the interest rate is, even if it's not exactly, you know, 10%, 5%, 1% along with what the bank is. So definitely these things are interrelated. Same thing for inflation. You know, if I'm saying $1,000 today versus $1,000 1 year from now, and you know, maybe we'll use some like historical example. The country goes to war and they print lots of money, and the value of the dollar decreases a lot due to an oversupply of money. That causes a lot of inflation, and so, you know, if we were to present the same example, maybe you would have to get paid $2,000 next year as opposed to $1,000 today to take that deal. But in times where there isn't a lot of inflation, maybe you would take, you know, $1,100 next year over $1,000. So again, discount rates are tied to inflation and tied to interest, but they're not the same thing. Okay. And so this equation down at the bottom shows the value of money today from value or based on the quantity of money in some future time. So say you're given, you know, $2,000 next year. How much is that worth to you today? Well, it depends on your discount rate. Down here, let me change my color. It depends on your interest rate here. And say you had so $2,000. say you had a 10% interest rate. So then if that was 1 year from now, that would be 1 plus 0.1, 10%, which is 1.1. And then n is the future year. So in current day, we say n is 0. 1 year from now, n is 1, and so on and so forth. And so this will give you how much money it's worth. So oftentimes you'll see equations that even if you're not looking, specifically from these lecture notes online, you'll find equations for like present value and future value. So just remember the best way to sort of like remember this type of equation. You don't need to memorize this thing, but future money is worth less. Current money is worth more. And so if I want to go from future to current, I have to, or usually you have to do a division, right? So I'm making my present value smaller by dividing by some number. And if you want to get to a future value from a present value, then oftentimes you are multiplying to make it smaller. Okay. Here's a couple, this is again kind of like a reference slide for you, but we'll go through it to make sure that folks understand. There are some kind of shortcuts that you can do. If each payment every year is the same, then you can calculate the present value across some set of payments via this equation, where it's the amount of payments divided by what's called the capital recovery factor. Okay, so let me describe kind of in a little bit more comprehensive detail what's going on here. Suppose you are paid $100 a year for 4 years. This is typically the strategy that I use to help visualize this. So if I'm in year 0, 1, 2, 3, 4, and I receive $120, or sorry, $100. I don't know why I said 120. $100 every year. In theory, I should be making a total of $400. I just add all of those up. But remember, the value of the money changes from every year to year. And so this $100 would need to be actually divided by, if we're at a 10% discount rate, this would be 1.1 like that, plus 100 divided by 1.1 squared, plus 100 divided by 1.1 cubed, plus 100 divided by 1.1 to the fourth. And so this will give the value of the currency if I did all this math and added it all up. The whole point of the CRF is to do a little shortcut. If the payments are constant, which they are in this case, if they're $100 every year, then I can just calculate this number here, the capital recovery factor, plug that in, and then I don't need to do these large summations. Okay, and so another term to keep in mind is the levelized cost. And so that is the constant cost that would be incurred annually over your time period. And so whatever present value that I have, it is normalizing the costs such that it's equivalent over time. And so it wouldn't be the 400 divided by into each of the years. It's the present value divided by each of the years. So you've already sort of discounted it. Okay, so back to that question of would you rather have $1,000 today or $120 per year for 10 years? Okay, so this depends on your discount rate. And so at a 0% discount rate, which is basically saying that the value of money at any point in time is the same, which isn't really true for anyone, then the value of the money would be just 10 times 120. And so you would rather take $120 per year because the present value is worth more than the $1,000. And then we can see how that changes as your interest rate increases, or not your interest rate, sorry, as the discount rate increases. And so we go up to 5%, up to 10%, 15%, and these will lead to present values that are smaller. Okay, again, to sort of build into your intuition, as your discount rate increases, right, that means that the value of money in the future is worth less and less, right? So $1,000 next year at a higher discount rate will decrease faster, right? Because I'm dividing by a larger number, right? Here you divide by 1.05. Here you divide by 1.1, 1.15, and 1.2. And so as these numbers increase in size, the value of the money decreases. And then you can see that the present value is also decreasing. And so even at 5% discount rate, you will see that the value of that money is worth less than $1,000. And so you would rather have the money upfront. This is kind of like a lottery problem, right? You can take an upfront payout versus annual payout over some amount of time, and because of concepts like discount rate, it's pretty much always better to take the upfront payout in something like a lottery. Yeah, so here in this bullet point, it's basically explaining that once you get to above a 3% discount rate, having $1,000 upfront is a better deal. Okay. CRF is the mortgage formula. Again, this is the annual payment required to repay a loan over a term of n years at a specific rate. If there's no interest, then the annual payment is just the loan divided by n. But if you do have a rate, you can calculate out the annual payment required using the CRF. Okay. I had really quickly talked about inflation. Again, this is the increase in costs without a corresponding increase in goods and services. This can be viewed with, in the US, we measure this with what's called CPI, which is a consumer goods index. Basically, they look at a quote unquote sort of basket of goods of typical things that you would spend money on, and they look periodically, every year, how the price of the items in the basket change, right? And so the types of goods and services that you're receiving will stay the same, but the price of those items will change over time, and that's known as inflation. So, back when I was in grade school, right, like soda costs $1, right, and that may increase now, $1.50, $2. So that's exactly the concept of inflation specifically for that good. So that's different from real escalation, where you can see changes in the costs and corresponding prices due to changes in demand or differences with the technology. And so it can be tricky not to conflate those things, and that's why inflation has this sort of standard index, so that other sort of price changes are happening due to other reasons. The nominal discount rate includes the effect of inflation, and so you might think of this as more of a traditional sort of interest rate. When we talk about a real rate versus a nominal rate, the real rate is the thing that excludes the effect of inflation. And so you can calculate the nominal rate by explicitly putting in effect of inflation with this equation here. We won't worry about this too much in this class, but it's a good concept to keep in mind as you think about looking at like historical prices versus prices today. You always need to be aware if you're looking at nominal dollars versus real dollars, because that tells you that includes the effects of things like inflation. And I'll show an example of that in a second. And so when you have a real discount rate, you use constant dollars. When you have nominal discount rates, then you have current dollars. Okay, so what is this? Current dollars are basically everything in terms of the dollars that was seen. And so if I go back in time at a specific time period and I pay for like a gallon of gasoline, whatever I paid at that time, that is the current dollars. But the worth of the money then compared to the worth of money today is slightly different. And so if we wanted to put those on the same basis, then we would have what's called constant dollars. And so these are often used for technologies over periods of time. And most of the analyses that we want to do when we're thinking about extending analyses over, decade and multi-year timeframes is that we want to keep everything in constant dollars. So you're really comparing sort of apples to apples. So inflation can double the costs if you don't use current dollars. So one example of this is gas prices. So these are gas prices for unleaded gasoline in Texas, stretching all the way back to the late 70s. And if I went back in time and I bought a gallon of gasoline in, say, 1980, I would have just paid $1. And you might think, well, that is way cheaper than gas today, right? Because if I look at the cost of gas today, we're talking about, well, let's say I go to, 2011, I would have paid something like $3.40 per gallon equivalent. But when I adjust for inflation, I can actually see here the cost of or the real adjusted for inflation price that I'm paying is actually pretty similar to what I would have paid in 2011. And so when we're thinking about doing analyses over these sort of long time spans, having your work being done in current dollars is going to be crucial to make sure that you're doing the right comparison. And so you can correct for inflation. Sometimes you have the data that you're working with might be cost data that is in 2003, but the analysis compares to a study in 2000. Then you can use something like a GDP deflator, or I think probably the best thing to use is the CPI. The consumer goods inflation index to convert between dollars. So like a price deflator for GDP might look something like this, where if I want to convert from, let's say, 2012 dollars here into 2017 dollars, you multiply by whatever dollar amount that you're working with by the ratio of the GDPs. So that's sort of quick, easy way of taking into account inflation over time. Okay, so back to thinking about discount rates. These things can have a pretty large impact on costs, and so what is the discount rate that that should be used? So this is the same example that I was talking to before, and you can actually elicit your own discount rates, right? And so if you really sort of sit back and think about this question realistically, like if I were to actually offer you $1,000 today, or you were to take, say, X dollars 1 year from now, how much money would you be willing to take or need to take for you to delay taking the $1,000 today? So this is a way that you can calculate sort of your own discount rate with this pretty simple equation. If you figure out what that X dollars is, then you can figure out your discount rate. And so if I were to say, okay, I will give you $1,050 next year, think about if you would take that, right? And at the point at which your decision changes, that's approximately sort of your sort of discount rate that we're able to elicit. And we calculate that essentially by solving for I. Okay, and what discount rate is sort of the proper one to use? Again, these vary from different entities. There's not one specific right answer. A more risk-averse person would typically have a higher discount rate, and a more risk or less risk-seeking would have a lower discount rate, and a higher risk-seeking would have a higher discount rate. So businesses often use higher discount rates because they are more risk averse, and they have like a broader portfolio of investments that they can maybe take advantage of. And so unless you're giving them like a really good deal, they'll often hold off because they're looking for things that that will make more money. And so their discount rates are going to be quite a bit higher. regulated utilities, for example, have a discount rate of about 6%. When we're talking about individuals, individuals typically have lower discount rates than businesses. So the typical rate that you would use is for an individual is going to be probably around 5 to 10%. And discount rates for developing countries may be even higher, right? 15 to 25%. And so that means that the value of money in the future is worth a lot less than it is today, again, at higher discount rates. Okay, so we're about halfway through. I'm going to take a pause here. We can do a quick 4 or 5 minute break up to 1 o'clock. And in the meantime, you can brood over what you think your discount rate is, or if you have any questions, now would be a good time to ask. And then we'll pick up again at 1. Sure, okay, so I see a question. Can you go back to the example of finding a discount rate? And actually, yeah, actually this would be a good time for me to do this. I'll quickly post the slides while we're waiting. Okay, I just posted the slides, so sorry about that, and hopefully you can access them now. Okay, so I see a question about the GDP table. So this is, it's just one So this table is just demonstrating one example of how you would be able to convert from current dollars into constant dollars. So these values, I believe, should be um, in current dollars, and so we're converting. Um, we're converting into constant dollars by taking the ratio of the GDPs, which is giving a sort of rough method of figuring out what the value of the dollars are between years. This is kind of actually this is probably less common to do it like this. These are actually some slides. Some of these slides are being recycled from the previous instructor, and this actually isn't how I would necessarily look for the conversion into constant dollars. I think that the CPI is probably a better way, and so you could just Google CPI calculator, and it'll take you to it should take you to a sort of generic calculator site that will be able to tell you the change in inflation from one year to another. And so you could look, you could literally just put in 2012 to 2017, and what it does is it looks at the value of that basket of goods that I was talking about before to sort of put everything from nominal or current dollars into constant dollars. Okay, so hopefully that clarifies that. Okay. Okay, so this is where I think it gets pretty interesting when we think about discount rates and future generations. The value of money will decrease over time. Okay, I feel like I'm keep harping on this, but think about it. How much is $1,000 worth to you today versus 100 years from now? Well, you're going to be dead probably, and so we don't value money that goes on into like long periods into the future, right? Every year, progressively, that the value of the money decreases, and so here we get to like a really fundamental issue when it comes to intergenerational problems like climate change. Okay, self-interested individuals and companies prefer money now rather than the future, okay? But when we think about something that could impact not me, but maybe my kids, then you put a lot less value into those types of problems. And it can be a difficult type of thing, right? Because when we think about climate change and we say, oh, why don't companies just kind of do the things that are best for future generations? Like even if they wanted to, right? Even if they say, okay, forget how we're valuing discount rates, and I'm gonna go and invest in things that may make less sort of financial or economic sense if we're really thinking about traditional discount rates, or even other sort of economic or financial instruments. Well, they may be altruistic, but maybe their competitors are going to drive them out of business, and that doesn't really sort of help anyone, right? And so this is one of the sort of more fundamental problems. And so economists and some philosophers have talked about how we can deal with this issue, about how we can put the welfare of future generations to think about on the same level, and depart from issues caused by the way we inherently value money. And this is a concept known as hyperbolic discounting, and it implies that public investments, when we think about at a societal level, should be discounting at really, really low percentages, at 0%, or even say something like 2%, so that we can make decisions, make economic decisions that will benefit long-term future generations, but maybe not as much us personally compared to other sorts of investment decisions that we could be making. And so these discount rates are the types of things that that the government would essentially try and propagate and promote. So when we're talking about individual time preferences, the relative weight for the value of goods and services, that's what we're thinking about on an individual preference. And we always prefer things immediately over things that are delayed, because if we take things immediately, you can do things with them that would outvalue whatever you would receive later on. But with an intergenerational time preference, so more of like a social society time preference, then the thing that you need to be caring about is the welfare of future individuals. And so this is the value that you may try to take when we're thinking about not yourself, but your kids or your grandkids, something like that. Yeah, and so there's actually a pretty interesting paper that sort of thinks about these issues, published back in the early 2000s. Okay. Going back to doing some of these calculations, some things to keep in mind: simple payback time. So this is just your initial investment divided by the number of years, right? And so if I were to, say, insulate my house and it costs $1,000, but it saves me $200 a year in utility bills, well, the payback time is just 5 years, right? It's $1,000 divided by 200, which means after 5 years, I've made my money back. So that's fairly easy to calculate, but it doesn't actually take into account the cost of the money, because I could be, suppose that you take the $1,000 and you maybe invest it in something else, maybe your return could be slightly higher. And so because the value of the money changes over long periods of time, this is not how you would want to typically approach this type of problem, especially when we're talking about energy and electricity for infrastructure and goods and services that last, many decades. Okay, so economic figures of merit, so life cycle cost. So the life cycle cost is the present value of all costs over the entire lifetime of the investment. And so this is kind of like the sort of payback period, except it's looking at including the changes in value of money over time. Okay, and so this is here. Let's see. The CC refers to the capital costs, and so the capital cost is sort of the initial sort of down payment for a particular item, and then you may have costs happening every year, um, uh, and that's CN. And you're essentially dividing by this interest rate um, every year that's changing over time. And this quantity here is essentially the same thing as we've been talking about in previous slides, where you're having sort of these annual payments happening over time, and we're able to sort of value that into a single present value. And then you may actually get a little bit of money back in your salvage. So this S is the salvage value. So whatever your item is worth at the end, you can sell it off and make some money. But of course, that money is going to be discounted by the lifetime period of whatever good that you're working with. Again, there's a fair number of these equations. But I'll sort of just kind of reiterate that that if you use sort of common sense, you won't need to memorize any equations or anything. You can pretty easily figure this out. So if I go back to the drawing or diagram that I used before, this is a pretty straightforward method to remember how this works. Again, these are referring to each of the years. So year 0, 1, 2, 3, 4, 5, and so on and so forth. Dot, 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 to say whatever my n is here. And typically, the way that I like to do this is I draw these arrows, and I draw down arrows for things that cost money and up arrows for things where I make money. So here in year 0, I have a big down arrow for the capital cost. So that's just CC. And then in years 1 all the way through N, I will have a set of down arrows. And if we say Cn is always the same, then it would just be something like this. Okay. And then in year N, if I sell whatever is left of my equipment for the S value, then I'll also have some positive amount S here. And so in the last year, the delta arrow would be something like this. If S is bigger than Cn, it would just be, S minus Cn. And then the thing to keep in mind is that every one of these years has to be divided by 1 plus I to the n. So this, I'll just start in year 3 because the text is making it confusing. So 1 plus I to the 3, 1 plus I to the 4, and so on and so forth. Let's see. Will these? Okay, I see a couple questions. Will we be given these formulas, or do we have to memorize them? You don't have to memorize them, and actually, it's not as though it's more important that you understand what's going on than to memorize the equations. For this class, since it's all online anyways, you guys are all going to be able to Google and look at the slides. But it is important to understand how to apply these formulas. And this formula here is equivalent to calculating everything that I've just sort of drawn in this diagram. Okay, I see another question. In the last example, if $200 is the CN, $100 is CC. Okay, so CC and CN are different concepts, right? So it would be sort of like, to take a more sort of personal example, CC, capital cost, is like if you were to buy a car, okay, you buy like a Honda Civic that costs $20,000. So CC would be $20,000, and then CN would be what you pay for gas and insurance and for maintenance of the vehicle. Okay, so actually, uh, let me pull up a whiteboard real quick. So if I were to take this example of a Honda Civic at $20,000 capital cost, and then let's say you have, let's say you spend $500 per year on gas, maintenance, and so on and so forth. So this would be your CN. Okay, and so, okay, let's say the car lasts 15 years. And at the end of the 15 years, you say you can salvage it. Is the value of the salvage, say, is $2,000. Okay, so you sell it used, for example. Okay, so I could plug this all into the equation, and you could just memorize this, which would be fine. That'd be 20,000 plus some from 1 to 15 for n. And that would just be $500 divided by, 1 plus, let's say our discount rate is 10%. So 1 plus 0.1 to the n, and then minus $2,000 divided by 1 plus 0.0, or sorry, 1 plus 0.1 to the 15th. Okay, and then you can calculate that number, and that'll give you the life cycle cost. Okay, and the way that I was just trying to visualize this again is with these sort of dots, right? Year equals 0, 1, 2, 3, so on and so forth, all the way till 15. So in year 0, you pay $20,000. In year 1, it's 500. In year 2, it's 500, and so on and so forth. And then in year 15, it's 500 payment, but you also get a big positive, and that's $2,000. So the delta would be plus 1,500. So here this is plus 1,500. And then again, we divide each of these by their respective discounting procedure, right? And adding all of these up, and so adding all of these up will give you the same answer as here, except that or just keep in mind that the signs are different. So usually I would say things below are negative, and things above are positive. Okay. So hopefully that is clear. So I'll go back to the slides here. And 1 second, I need to bring my chat back up. Okay. So operating costs, if the costs are the same each year, you can do the capital recovery factor, right, which will help us annualize everything. And so this CRF is an easy way to translate those arrow costs across time into an annualized operating cost. It's a way to simplify some of the calculations. If your costs are changing every year at a constant rate, you can have some kind of equation that will modify those arrows. So this would be something like in my example where I was drawing the arrows. If they get bigger at a constant rate every year, you can do this modification to change the costs. Okay. I wouldn't worry too much about this, and again, these are sort of more sort of shortcut equations, but as long as you understand the concept, that'll be kind of the most important thing, right? You could always figure out how to do this if you understand what's going on rather than sort of just memorizing the equations. Okay, and so besides the capital costs, right, you may have some fixed and variable operating costs. So fixed costs are things like operating labor, total maintenance cost, overhead, and then variable costs are consumables that depend on the amount generated. So, okay, what might this be? So in the example of the car, a fixed cost might be something like oil maintenance, right? So it's kind of variable because they tell you, oh, get your oil changed every some number of miles, but it's also kind of fixed because they say get your oil changed every 6 months or whatever the amount of time is, right? So if we think of more on the periodic time thing rather than the mileage, then that would be considered a fixed cost. Whereas a variable cost might be something like the cost of gasoline, right? And so the more you drive, the more gas you consume. The less you drive, the less gas you consume. And so the variable operating costs will change year to year as you drive more and less. For something like a power plant, fixed costs would be like the employees, right? And so the employees who work at the power plant, it doesn't matter, if the power plant is on and off a certain amount of time, you still have to pay all the employees. So that would be like labor costs that are fixed. But if the plant is on more often than it's off, then you are paying more money for the fuel that you're burning at the power plant. You could be paying more water for, especially if you're using like a boiler or something like that. The pass-through volume is going to depend on how much power you're producing. And so you'll have annual costs that will stay the same every year, and you'll also have a set of annual costs that will be varying every year. For something really large, for a large purchase, for an individual, this might even be like a car, right? It's pretty rare that someone goes in and just pays the entire value of the car sort of as just right at the transaction point. Oftentimes you finance the car, right? And so this is a similar concept with power plants. We call the overnight construction cost. So an overnight cost is something that you would pay to build the plants basically all at once. Okay, and so if it could all happen, then the money that you pay to make that happen in a single night is called the overnight construction cost. It gets a little bit more complicated because oftentimes it can take a couple of years to build a large power plant or energy facility. And so you oftentimes spread those out over time, and you're borrowing money to build it. So suppose the plant costs $150 million, it's built over 5 years with an interest rate of I. The total cost would be something like this, 150 million, where you are 150 million over 5 years, and each year progressively is affected by some kind of interest rate. And so at an interest rate of 10%, the total capital cost for what's called the allowance for funds used during construction, the AFUDC, is equal to actually $200 million rather than $150 million. And so this is a function both of how long it takes to finance the project and what the interest rate is. You can have recurring capital costs. I think this is kind of a weird nomenclature. Oftentimes we'll call this this can be part of the like fixed costs. So you might actually think of this as part of the like operations and maintenance. So the fixed variable costs. Again, all of these terms are like they're not so relevant as long as you sort of understand the concept. So in this particular example, a car lasts 12 years, but the tire must be replaced every 4 years. The tires cost C0 are replaced at years 4 and 8, and the discount rate is I. So then you are doing the C0 times each of your respective discounts in each of the respective years where you have to replace the tires. So going back to my little diagram here, if this is year, say 0, 2, 4, 6, 8, in this case, I'm going to have an extra set of costs at years 4 and 8. So if you have your CC here and your CNs here, you may have this extra thing, C0. So this is CC, CN. Then at years 4 and 8, maybe I'll have another extra arrow, which would be C0, something like this. Okay, and then you could just add those up for the total. So same type of concept. We're introducing a couple more definitions, but really if you can keep this straight in your mind about how I would sort of add them in that diagram, I think that's the easiest way to track this. So annualized life cycle costs. So this equation here, it's the same as before, where you have the LCC, which is the sum of your capital costs plus your annual costs and maintenance for both fixed and variable operating costs, right? That's this part here, plus your salvage costs at the end here. Except now you can annualize it with your CRF formula. And so if you multiply your CRF against the total costs, your total present value of everything together, right? And so this is thinking about, you know, the cost of the car plus the cost of the gasoline and all the maintenance, and then discounted to present value. I can annualize that via the CRF. Note that in this bottom equation here, this C0 has been multiplied with the CRF, it's not, it's being simplified. And so if Cn is constant, it's just saying we'll have that as this value. I'm not the biggest fan of this particular type of equation. I think it's a little bit less useful, because essentially what it's saying is that the annual costs translating from here to here, you're just saying Cn is equal to C0. And so you aren't actually doing any discounting here, right? So it's the reason why you do this is because it makes the calculations a little bit simpler. But this misses out on the whole idea of the time concept of money. So the best way that I can describe what's happening here is that if I do going back to my diagram again, as you do each of these, well, the issue is that where we would normally divide by yeah, I see that. I'll get to that in a second. So as we divide by normally this is what we would want to do, right? Oops, not I, N. We would divide by the 1 plus the discount rate in whatever year it is. But the third equation makes it so that you don't need to do that. It just gets rid of the discounting issue. So it makes the math a lot easier for sure. But I don't think it's a great representation of how to actually keep track of the money. Okay, so in the question, so in this case, the C0 in the second equation is the same as the Cn in the first equation. That's exactly right. So that is basically saying this, let's see, this value here is the same as this value. And there's a question, do they have the same meaning? So no, so actually, so this, I really should write this as simplified ALCC. So these, yeah, sorry, these equations are not the same. Okay. So this is only applicable if you pay your, yeah, so the other thing is that it's annualizing our capital costs, which is a fair assumption, but it's only applicable if you pay your capital costs annually. And so sometimes, so in this example, sometimes some problems will have your CC like this, and then sometimes it will redistribute the capital costs into annual components, which is what you're doing in the annualized equation. Okay, so there is an important sort of concept that is very commonly used in energy economics called the levelized cost of electricity, or levelized cost of energy. And the reason why we do this is if I think about power production, power plants, and the like difference in sizes and the vastly different amounts of costs, how do you go about figuring out a good way of comparing like a coal plant to like a wind turbine to even maybe like an energy efficiency measure? If I were to do this previous equation here, the annualized life cycle cost for a coal plant versus like a couple wind turbines, the life cycle cost is always going to be a lot larger for the coal plant, but it also produces a lot more energy. So it's not necessarily a good comparison. And so there's been a lot of sort of different ways to try and compare them in a more sort of apples to apples manner. And one of the most common ways is this way, with the levelized cost of electricity. So it's exactly the same as before with the annualized levelized cost, but it also then divides that quantity by the amount of energy that you produce in a year. So what are the units of this thing? It's dollars per year divided by kilowatt hours per year. So it's essentially giving, if I take into account how much it costs to build, how much it costs to operate, and the lifetime of this thing, I can, and how much electricity it's producing over the lifetime, I can approximately say, okay, this is how much it costs me to produce like 1 unit of electricity. And if I do that same thing for many different technologies, now I have some basis, a better basis with which to compare them. So this is like the second equation in the previous slide. This is like the third equation. This is the simplified. And then I would say this is more of the sort of proper equation. This is the same. The equations 2 and 3 are the same, except that it's saying C0 and Cn are the same, and then you are getting rid of the discounting at the bottom. Okay. It's also gotten rid of the scrappage or salvage value, but that's usually pretty easy to sort of tack on the end if you need to. So again, just as a reminder, these are not the same. Okay, how do we calculate the average energy production? And what is this concept of capacity factor? So the average energy that you produce in a year, we can think of as kilowatt hours per year. So the capacity of a plant is basically telling you how big the power plant is or how much power it can produce in total. So that's the maximum output. And so if I ran the power plant full time for 8,760 hours, so that's 8,760 is a very useful number to keep in mind. That is 24 times 365, which is the number of hours in 1 year. 8,760. The capacity factor tells us how often that power plant is on. And so it also, so say you're running at 80% capacity, that means across the full year. The 80% you can multiply by the capacity or multiply against the hours of operation. It'll give you the same answer. And that tells you how much power is produced across a full year in kilowatt hours per year. The capacity factor is never at 100%, okay? And that accounts for the fact that they're not on all of the time. Sometimes the demand could be lower, right? And so if you think about the amount of power that is, or sorry, the amount of energy that is being demanded by a household at 4 p.m. on a hot day when you have your air conditioning running versus 4 a.m. when all your lights are off, everyone's sleeping, right? The amount of demand will change quite a bit, and therefore there will be some power plants that are off, some power plants that are operating at lower capacity when there's lower demand. You could have planned or unplanned outages. This is a little bit less common, although we saw some of that last year with the fires. And then you could have things like intermittent power, so things like renewables where you have wind or solar, right? If the sun isn't shining or if the wind isn't blowing, it's not going to be producing at its capacity. So to give a rough estimation, I'll give some more accurate numbers in future lectures, but just sort of for your reference point, capacity factors of nuclear power is usually 90+%. These are really considered what's called base load. They're almost always on. You only really turn them off for maintenance, and part of the reason is it's a lot harder to bring to turn off a nuclear plant to take the control rods and neutralize them for periods of time, and so nuclear is almost always operating at the highest. Coal will operate between 60 to 80% roughly. I need to sort of double check how accurate those numbers are these days, because coal power has been really dropping in the last couple of years. But generally, coal is also considered base load. Natural gas is the next sort of big one. These guys will operate very sort of widely. There are some plants that are on quite a lot. There are some plants that are on not very often. And so these guys are going to be anywhere between, I would say on average, 30 to 80%, something like that. And then wind/solar are going to be capacity factors of less than 30%. 30% is probably the 35% for wind is probably the sort of highest. Maybe you might see some examples of 40%, but that would be fairly unusual. Solar would be really high at like 20 to 25%, but you're usually talking about 15% on average for most places that have solar installed. Okay, So this is reiterating, again, simplified, right? Because this term is not discounted. Okay, so let's do an example so that everyone can see practically sort of how you would go about calculating this. Okay, so the capacity of the plant is 1,000,000 kilowatts, 1,000 megawatts, or 1 gigawatt. Wind will have a wind farm that's operating at okay, actually, sorry, not a wind farm. This 1 megawatt would be equivalent to one turbine. Okay, so one turbine versus a coal plant. The capital cost is $1 billion for the coal plant, $1.5 million for the wind plant. There's fixed operating costs, so this is related to labor, maintenance, that sort of thing. There'll be 4% of the capital costs, and then variable costs. So this is the cost of the coal, and then we also have to translate the coal into electricity. And so this term here, it's known as a heat rate. The thing that you can that you'll see from the heat rate is that it's always given in terms of some kind of unit of energy for gigajoules, or MMBTU are the most common, into units of, so this is fuel energy, into units of electric energy. And that's going to be kilowatt hours or megawatt hours. This heat rate is the plant efficiency. And so if you remember back to, I think, lecture 1, this is what we would refer to as an efficacy, because the units aren't the same. But power plant efficiencies are most commonly referenced as heat rates. So this is a pretty common type of thing that you would see. Okay, we have capacity factor, 70% for the coal, 35% for wind. They both last 20 years, and we have a discount rate of 10%. Okay, so let's go to a whiteboard and figure out this calculation. So we'll do this real quick. Simple LCOE is equal to CRF times CC plus CO. Capacity times 8760 times capacity factor. Okay, so let's calculate each of these sort of one at a time. The CRF at discount rate of 10%, lifetime of 20 years. Okay, so this, I kind of lied. This is an equation that you would, I guess, need to memorize or reference. It would be sort of harder to derive. Oh, let's see. I guess it got erased. Oh, here we go. So this, I'll just pull up the, I'll just use the equation from the slides, but this, again, this is something that you would be easily able to reference yourself. So this is I over 1 minus 1 plus I to the negative n. So that's equal to 0.1 over 1 minus 1.1 to the negative 20, which is equal to 0.1175. So that's our CRF value. So the capital cost of the coal was equal to $1 billion. the capital cost of the wind was equal to $1.5 million. Okay, and now we want to calculate the C0. So for coal, C0, let's say of coal, is equal to, there's two parts. There's the fixed value, which was the 4% of the capital cost. So this is 1,000 times 10 to the 6, $1 billion, times 0.04. So this is fixed plus, we need to know how much it costs to produce all the power that it's making, the variable cost. So the amount of power that it produces is 10 to the 6th kilowatts times 8760 hours times our capacity factor of 0.7. Okay, and so this will tell us the kilowatt hours produced by the power plant. Now I'm going to multiply this by 0.009 gigajoules per kilowatt hours. So this is the heat rate. Okay, so this amount of electricity, this is heat rate, aka the efficiency. So it's going to turn the amount of electricity that we produce into an amount of coal energy that's needed. Okay, let me get rid of this and this. Okay, and then the amount of money was $1.2 per gigajoule. Okay, and so this whole thing here is the variable cost. And if I add up all of that, that's going to be 106, 225, 600. Okay. And then let's go to a new whiteboard. The CO of wind is a little more straightforward because it has no variable cost. It only has fixed costs. So that's 1.5 times 10 to the 6th times 4% is equal to $60,000 per year. Okay, so then we can calculate the simple LCOE of coal, and that's equal to 0.1175 times, so this is the CRF, 0.1175 times 1,000 times 10 to the 6, which is the CC, so this is CRF, this is CC, plus that number that we calculated, 106, 225, 600. This is C0 divided by 10 to the 6th kilowatts times 8760 hours times 70%. So this portion here is electricity produced. And that total is equal to 0.036 per kilowatt hour. So it costs about 3.6 cents per kilowatt hour to produce electricity from this coal plant. Really quickly, if I do the same thing for wind, you will find that it's a similar order of magnitude, which is good. So calculating in the same way. Okay, hang on, let me see, I see something in chat. But that amount is different from what each household pays for that electricity. Yeah, I can touch on that in just one moment. Oops. Hour times 0.35, and that's equal to 0.077 kilowatt hours. Okay, so this is the final sort of levelized cost. It's the most sort of apples to apples comparison of the cost of electricity being produced from a coal plant versus a wind plant. These numbers are probably a little bit old, and actually wind so natural gas is more competitive than coal, which means it's lower cost, and actually wind these days is probably more on the order of natural gas than coal. So probably these numbers are maybe even reversed by now. But at least this whole example is just to give a sense of how to do the calculations. Okay, so I see this question from Natasha that the amount here is different. Is that the same or different from what the household pays for electricity? It's different. So this is a cost, remember, and what you pay is a price. And we will later talk, when we're talking about electricity grids, about how these sort of prices play a role in determining, or these costs play a role in determining the price that you pay for electricity. But you're correct in that these are not the same thing. Okay, let me go back to the slides really quick. I need to see how many slides we have left. I'm going to stop here. Yeah, I'll just touch on this as sort of the last slide for today. Yeah, sorry for keep running into the time limits, because this is the first time I'm teaching this class, so it's I'm needing to gauge how long it takes to get through all these slides. But we'll end here for today. This is a nice little chart of real data of ranges of levelized costs for different fueling technologies, and so you can see how much it costs for coal, which is this one right here, IGCC, versus wind, which is onshore wind, which we actually say is lower than coal. These are 2020 projections from 2015. And there are a couple tools that are actually pretty useful. You guys can take a look at some of this documentation and online tools that provide you resources with how they're calculated. I'll talk a little bit more just really briefly at the beginning of next class about some things to consider when you're doing levelized cost of energy. But at the end of the day, I think this is a pretty useful metric for being able to compare costs across really sort of different energy producing technologies and mechanisms. Great. Okay, so why don't we end here for today? And before I end, I'm happy to stick around and answer any questions that folks may have. So I'll probably just wait 1 or 2 minutes and take questions.
Oh, okay. So going back to like the question you had, or the example you had in the beginning of
Mhm.
the lecture, um, real quick about sig figs, you
Yes.
said, I mean, in these examples, the efficiencies ended up being like the lowest, but
Uh-huh.
for example, the 30 kilograms of the dry biomass at 35%,
Yep.
why wouldn't you look at the 30 kilograms? Isn't that just one significant figure, technically?
Yeah, actually, that's a good point. It's actually it's actually two significant figures, but this is where I kind of give the most flexibility, because oftentimes when like round numbers are reported, it's hard to tell like the level of significance. So actually,
Yeah.
I'll just really quickly uh, write down. So if technically the way that you would write one sig fig for 30 would be like 3
Zero.
times
Oh,
10 to the 1 kilograms. Um,
okay.
and that's one sig fig. If you write 30, technically it means 2 sig figs. Um, but that kind of varies. Like it could be that it's actually 30 plus or minus 1, or it could be that
Yeah.
they're kind of they just rounded, and they're being flexible. So when it comes to round numbers like this, like what if they wrote like 1,000 kilograms? Like, does that mean that this is 4 sig figs? Um,
Yeah.
pr- uh,
I thought that they would like for it to count as four. I thought they would put like 1,000 like period.
uh, oh yeah, I have seen that. Although that's pretty uncommon. That's like, so
Okay.
yes, I do know, I do know what you're referring to, but I've actually really, really rarely see that. So I tend to
Okay.
be a little bit more flexible. Like if it's like this, I wouldn't say that it's 4 sig figs, but I would look at other inputs to sort of contribute to that. I think that if it's something like on the homework or something, you could just like say that you could say that you're assuming some number of sig figs. Um,
Oh, okay.
but I'll look back over the ways we ask the questions, and make sure that is as clear as possible. So if I do mean for this to be 4 sig figs, I would write, or if I meant this to be 1 sig fig, I would just write 1 times 10 to the third, um, versus 1.0 times 10 to the third, right? So
Yeah.
I'll try my best to make sure that the homework at least will be like that. And Facundo, hopefully, if you're still there, hopefully you can check that when I send it to you.
All right. Thank you.
Yep. Um, okay. Barring any other questions, I'm gonna end for today, and hopefully I'll see everyone on Wednesday. Thanks.
See you, Adam.